All right, well, we've been talking about lines, equations of lines, so on and so forth, and now we want to switch our focus and talk about planes. And so intuitively, a plane is just a flat surface. Typically, when you want to draw a plane, you somehow put a little boundary along the plane just to be able to see it, but we need to understand, unless otherwise specified, the plane extends forever in all directions. It isn't actually just a piece of a plane, it's the whole plane going forever in all four of those directions. So similar to a line, a plane is also determined by a single point and a vector. And so let me show you visually what we need. We need a point on the plane, and then we need a vector. I'm going to think of it as the flagpole vector. It's called the normal vector, but a vector that is orthogonal to the plane. So it's perpendicular to the plane. It's coming straight up like a flagpole would. And I'll even draw a little flag on here, something like that. There's our little flag. Okay, so that's the idea, is that you need a point on the plane, and then you plant your flagpole on the plane as well. So let's be a little more formal now and discuss, let's discuss the setup. So we're going to let P naught be a point on our plane. And we're going to let n, which is a vector, we'll just say ABC are the coordinates. So n is a vector that's orthogonal to the plane, and this is called the normal vector. All right, and so like with lines, I want to somehow visualize the origin down here to the side. So let's put that there and there and there. So this will be my origin, and here's my point P naught sitting on my plane. And I'm going to go ahead and again think about, I'm going to switch perspectives on P naught. There's a corresponding vector R naught that I'm going to want to think about. I've got my normal vector N shooting up out of my plane, something like that. So there's N. And now I want to pick another point on the plane. We'll call this point P. And I want to think about the vector form of P as well. So I'm going to let that be R. And so let's think together. What does it mean for P to actually lie on our plane? Well, because it's on the plane, we can form a vector from P to P naught. Actually, we can always do that, whether or not P is on the plane. But form that vector from P naught to P. And now look at the angle between those two vectors. And if you think about what this normal vector is, what the flagpole is, it's orthogonal to the plane. And so that means that if P is on the plane, then the angle between those two vectors should be what? It should be 90 degrees, right? And how do you check if these two vectors are orthogonal? You compute their dot product. Their dot product should be 0. So that's the situation. Let's actually maybe fill in this vector, and we can, oops, let me try that again. We'll do that. There we go. Okay. And so we can write down P, the point P. By the way, P is, for me, just some arbitrary x, y, z. And then so R is just the vector form of x, y, z. And just to be crystal clear, R naught is the vector form of the point P naught, so x naught, y naught, and z naught. Okay, so that's the situation. Let's slide this over so it's a little less confusing. So P lies on the plane if and only if the vector, now let's be careful, we could describe this vector as the vector, let's actually write it this way, P naught to P, we could do that. But we can also get much more specific, right? This is a vector, this is the vector R naught, this is the vector R, and so you should instantly recognize what that third vector is. We tried to hammer that back in the earlier sections. That's exactly the vector R minus R naught. So this vector right here is R minus R naught. And so now let's write it out. So P lies on the plane if and only if this vector and this vector are orthogonal. And so that the vector that we're interested in is R minus R naught. I want that to be orthogonal to the normal vector N. Well, that happens if and only if, think about it, R minus R naught dot with the vector N is 0. And now if we want to, we can distribute that dot product, and we get R you know what, instead of doing that, let's actually switch the order here just because we can. Let's write this as n dot r minus r naught. That's just purely for convenience sake. And now at this point, let's actually write down what each piece is. So n, we said, was the vector a, b, c. And then think about it. This is x, y, z. And this is x naught, y naught, z naught. And so I get x minus x naught, y minus y naught, z minus z naught equals 0. Oh, great. Now I can take the dot product, and I get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And so this is called, or this is the equation of the plane. So this is a scalar equation. Please realize that. Even though we started with a dot product spit out scalars. And so it shouldn't surprise you. I get this scalar equation. And so this is the equation of a plane. Let's write it down. Let's actually say that. This is an equation of the plane that goes through the point x naught, y naught, z naught. And we'll say with normal vector A, B, C. Okay, so you can see the normal vector sitting in front of each of those terms, and then you can see the point on the plane as well. And it's important that you can recognize that. So one more thing, sometimes it's convenient to go ahead and multiply through, and so you'll get AX, right? A times X plus A minus X naught, B times Y, B minus Y naught, CZ minus Z naught. And the point is, when you do this, you'll get AX plus BY plus CZ equals some D. You can, if you multiply, this is a number, this is a number, number, and bring all those numbers over, that's your D. And so that's one way that you can write planes. So this is another form of the same thing. And so this, let's just say this is another way to write the equation. Now, when you write it this way, you've simplified a lot of the stuff, but you've lost the point on the plane. You can't see it anymore, but of course you can generate points on the plane easily. So in either case, you can see those normal vectors sitting right there. All right, well, at this point, we are ready to do an example, so I think I'll end this video and we'll do the example in the next video.